Welcome to the first in a series of screencasts dedicated to network application development with Node. This section will provide tips for installing Node. We'll also look at installing modules for your app using NPM, the package manager that comes with the framework. Finally, we'll highlight essential Node patterns as we break down a simple web server. Throughout the course, we'll take note of conventions you should follow while creating your app. After this section, we'll dig deeper into package management and event-driven programming. In later sections, we'll make extensive use of events when working with file streams and implementing the features of a typical web server. In the second half of this course, we'll leverage high-level frameworks like Express to build web applications that can store data, render views, and communicate in real time. You can find all the examples for the videos in this course on GitHub. You can get Node from nodejs.org/download. For Windows or Mac, you can automatically install Node using a wizard. To install Node manually, download the source files from the website. You can also use wget or curl to download them from the command line. Unzip the source files, then configure, make, and install. This will install the Node executable to your system, located at /user/local/bin/node. To manage multiple Node installations, try NVM, or the Node Version Manager. After installing NVM with this command, you can easily install any version of Node. Whatever installation approach you choose, you can verify that Node was installed successfully by checking the Node version. You can also start using Node by interacting with its command line interface. For a more useful example, we'll make Node respond to HTTP requests. Here's a JavaScript file with code for a very simple server. We can start the server by passing the file name as an argument to Node. With this server running, any request to a localhost URL on port 8000 will return hello world as a plain text response. As you can see in this example, we require or import the HTTP module in order to create the server. Node apps rely on modules for importing libraries. A module can correspond to a single file or a collection of multiple files and folders. Since the HTTP module is a core module, it can be required without explicit installation. Modules not included with Node can be installed with NPM, Node's de facto manager for packaged modules, or packages. In most cases, you'll install packages locally in your project's working directory. For example, this will install _. You can use the -g flag to install packages globally, typically in /user/local. In general, if there's something you want to use in your program, then install locally. But if you want to use something in your shell, then install globally so that its binaries will be made accessible via your path environment variable. Now that we've learned how to get Node running and install modules, in the next screencast, we'll take a closer look at how our simple server example works. In the last screencast, we installed Node and got our feet wet by running a simple server example. In this screencast, we'll take a bit more time to analyze what's happening in that script. In the process, we'll learn more about the HTTP module and see how callbacks play a crucial role in even the most trivial network application. As you may recall, the first thing we do in our script is import the HTTP module. It's one of the many modules built into Node. The JavaScript source for the HTTP module can be found among the build files we downloaded for Node. Back in our script, executing the require method will return the HTTP module as a JavaScript object, which we will assign to a local variable. We'll then use the createServer method of the HTTP module to return an actual server object. The createServer method expects a single parameter for the request listener function. In this case, we'll define the parameter with an anonymous function. Since functions are first-class objects in JavaScript, they can be passed around as you would any other value. When used in this way, the anonymous function is often referred to as a callback. This function will be executed at some point in the future whenever a request is made to the server. Once we invoke the listen method on our app, Node will start monitoring that port for requests. Whenever the app receives a request, our anonymous function will be automatically called back by our app. Each time our callback function is executed, the HTTP module will pass two objects as arguments to the function. One object containing data about the current request being made, and another object with methods for sending a response. In this screencast, We deconstructed our simple server example to illustrate fundamental techniques we'll be using throughout the course. We took a peek at the code contained in the HTTP module and imported it into our app in order to create a server. Finally, we started taking advantage of callbacks to respond to requests made to our running server. In the next section, we'll discover how to create our own modules and manage packages with npm. In the first section, we covered some of the basics of application development with Node. Along the way, we touched upon the topic of modules. In this section, we'll learn not only how to import modules, but also how to create and publish our own. Finally, we'll take a tour of some essential npm commands and review a few tips for managing dependencies. Building any large application demands effective scope control and file management. This is a challenge for a language like JavaScript since all scripts are forced to share the same global namespace. Node gets around this limitation by implementing the CommonJS specification for Modules 1.0. By implementing this standard, Node makes it possible to maintain local scope within a module and export a variable to another script, all without polluting global scope. In its simplest form, a module can correspond to a single file, for example, a configuration file. A module can also be an aggregate or package of multiple modules. External libraries are often made available as packages. To illustrate how modules work, let's take a look at an example. In Node, any module you import corresponds to a JavaScript file. Within a module file, the variable module.exports, or its alias exports, is used by the module to expose the properties and methods of its API. In turn, the script importing the module calls the require function to access the exported API. In this case, we assign an instance of an object to module.exports. What if we wanted to configure how the object gets created, or trigger a callback once the object has finished initializing? As an alternative, we could assign a constructor to module.exports and instantiate the module as a separate step. Although exports and module.exports are often used interchangeably, there's one important difference. In a nutshell, Node doesn't export the object currently referenced by exports. Objects and functions can only be exported by module.exports. If we change our example to use exports, we'll get an error. In order to make our example work with exports, we would need to assign the reverse method instead of returning the object. Regarding scope in modules, any variables not assigned to exports and declared with the var keyword will remain private to the module. Any variables defined without the var keyword will be global and will therefore be accessible to other modules included in your app. You can also use the global namespace object. However, relying on globals violates the principle of encapsulation and should be avoided unless absolutely necessary. In this screencast, we learn how modules export properties and methods to another script. In the next screencast, we'll learn the difference between core modules, third-party modules, and local modules. We'll also look at Node's conventions for locating the modules we're importing. At the beginning of this section, we learned how Node modules expose their internal API through module.exports. In this screencast, we'll discover the different types of modules in Node and the various methods Node uses to resolve the module identifier passed to the require function. Core modules can be found in the lib folder in Node source directory and documented on nodejs.org. Core modules are built into the Node executable and will always take precedence over another module of the same name. In other words, importing the cluster module will load the built-in module even if cluster.js exists in your local directory. Local modules are any custom modules you create for your application. Third-party modules are created by other developers and imported via npm. The string parameter we pass to the require method is called the module identifier. The identifier may or may not contain the .js extension. If no matching file is found, Node will search for a file ending in .js, then .json, then .node. A .node file is a binary add-on. If this module identifier is a relative path, that is, it starts with // or //, then Node will search for the file relative to the directory containing the script being executed. If the identifier is an absolute path, starting with /, then the module will be located relative to the root level of the system. If the identifier doesn't include an absolute or relative path, then Node will check for a core module for that name. Failing that, it will look for the file inside the node_modules folder within the parent directory of the file calling require. It will keep searching up the directory structure all the way to the root of the tree. Note that Node only searches in one direction. If our script were in Node demo, trying to load some util would search in the Node modules folder that is a direct child of Node demo, but not in the Node modules folder inside utilities. This method of locating files enables modules to have local dependencies, preventing conflicts when multiple versions of the same module are included in the single project, for example. If the module is still not found, then Node will look in the absolute paths listed in the Node path environment variable, as well as the following locations. In addition to loading a file as a module, we can also load a folder as a module. To accomplish this, we need to provide Node with a point of entry for finding the module. One approach is to use package.json, a package descriptor file that allows you to load a file or directory of files based on a single module identifier. When used for distributing a package, the package.json file acts as a manifest, describing both the library and its dependencies. We'll discuss package.json in more detail later in the section. For now, we'll stick with a simple example that acts as an entry point for Node to locate a module. In this case, the identifier myLibrary will resolve as /lib/coolLibrary, since it was defined as the main module within our package.json. If we don't use a package.json file, Node will look for an index.js or an index.node file. In this example, string utilities gets loaded from /nodemodules/stringutilities/index.js. As a reference, the previous examples assume the following directory structure. As a final tip for loading Node modules, it's possible to determine if the current file is the one being run directly by Node and not imported by another file. This might be useful if you want a module to do something differently when executed by a test runner, for example. To detect this, we can use the following conditional. In this screencast, we focused on the different strategies we can use to load modules. In the next screencast, we'll cover some tips for managing dependencies among third-party modules. In the last screencast, we got some insight into how Node locates modules on our system. In this screencast, we'll take a brief look at how to manage dependencies between third-party modules. It may seem confusing at first that Node doesn't have a central location to put modules. However, this turns out to be very useful. Let's say that we built an application that makes extensive use of the underscore module. What if underscore gets an upgrade that breaks our app? Fortunately, Node gives us the ability to load different modules within multiple node_modules directories. For example, let's say we had two parts of our app using an older version of underscore, registration and search. To avoid having to upgrade underscore in both places right away, we can keep the older version of underscore in registration and only install the newer version in search. This would allow us to use both versions in parallel without conflicts. As mentioned in the previous screencast, you can declare dependencies for a package using package.json. We'll discuss this technique in detail at the end of this section. For now, it's enough to know that packages are able to manage their dependencies internally using package.json. This is how the dependency declarations might look for the two modules in our example app. In this screencast, we learned how different modules in an app are able to safely use multiple versions of the same module without conflicts. In the next screencast, we'll review some useful npm commands to help us manage the modules we've installed. In the previous screencast in this section, we focused on what makes modules work and various techniques for loading them. In this screencast, we'll review some key npm commands to help us manage our modules. To show packages currently installed in our working directory, use npm list. To show packages installed globally, use the -g flag. npm list will also report whether the installed version of your package does not meet the dependency version requirements in your package descriptor file. Given the following file, this is what we would see if we run npm list. Notice that this module does not meet our version requirements. There's also a command called npm view to inspect a module based on its package descriptor file. By default, it will tell you everything in the package.json file from the latest version in the registry, not the version you have installed. If you want to know the dependencies for a given module, npm view gives you access to that specific property. To find out if newer versions of your module dependencies are available, it appears that npm outdated doesn't work as expected. Instead, you can also install the police tool. Once you have it installed, you can run it like this. Then, you can find out if any dependencies in your app are not up to date. To update a package, simply run npm update for that package name. To find packages, you can execute a query on the command line using npm search. You can also search the npm registry at npmjs.org. And another great option for discovering new and popular modules is Node.jsmodules.org. In this screencast, we took a whirlwind tour of some essential npm commands and discovered a few ways to find modules. In the final screencast of this section about modules, we'll learn how easy it is to publish our own package. In the last screencast, we got acquainted with some important npm commands. Earlier in this section, we mentioned that the package.json file can be used to load a folder of module files by defining the location for our main module. In the final screencast of this section, we'll take a closer look at npm's package descriptor file and how it's used to publish packages. We're able to install modules, frameworks, and applications with npm thanks to its inspiration from another common JS specification. At the heart of this specification is package.json, the package descriptor file. This file provides Node with all the vital facts about an application or module inside an application. By running the npm init command, we can generate a boilerplate package.json file. First, we need to create a folder for our module in the Node modules directory. Then, create a README file. It's always a good practice to provide documentation for your app, and npm will warn you if you neglect to include this file. Now, we're ready to run the npm init command. The wizard will prompt us for key properties of our app, providing sensible defaults for each. First, we get prompted for the name of our app, or module. This is what we would use as the module identifier. Next up, our version and description. Then we'll be asked for the entry point. This is the file that gets loaded when we pass our module identifier to the required function. Finally, we're asked for our test runner and a series of optional details about our package. Once we've accepted these settings, npm creates a new package.json file for us. Assuming we already have an index.js file in this directory, we can import this module from a script just like any other module we've imported so far. Let's run this app to test that our module is working. Another advantage of using a package.json file is that you can declare dependencies for other modules, in addition to the required Node version. This means that you'll be able to use npm to install your module along with the correct versions of all the dependent modules. By using the npm publish command, you'll be able to add your module to the npm registry. If you don't want your package published, then set the private property to true. If you need to declare something other than an exact version for a module dependency, there's a variety of formats for specifying version dependencies. You can use a comparator to allow any major, minor, or patch version greater than a minimum version. To limit your risk of being affected by breaking changes, use the X format to specify dependencies relative to a major version. To really play it safe, you can limit acceptable versions to a combination of both major and minor versions. See npmjs.org/doc/json.html for a complete list of options. In this section, we learned a lot about modules, from creating and importing to configuring and publishing. In the next section, we'll tackle an equally important feature of Node, events and evented I/O. In the previous section, we discussed how modules provide the benefits of code organization and encapsulation. In this section, we'll discover how events unlock Node's potential as high-performance server architecture. To start things off, let's examine the heartbeat of any Node application, the event loop. As revealed earlier, Node is able to handle many connections on a single thread because it is event-based. The feature that makes this possible is the event loop. It is a programming construct that regulates the control flow of any Node program. In simple terms, it waits for events and dispatches event handlers. The event loop executes callbacks one at a time. The code that gets executed for each callback will run without interruption. To illustrate how the process works, let's imagine a series of requests to a Node server that trigger an intensive operation of some kind. To prevent these operations from blocking execution, Node performs the intensive operation asynchronously. When the operation is finished, Node will invoke the callback supplied by the request, enabling execution to continue within the calling script. Just to be clear, asynchronous operations handled by the event loop aren't necessarily initiated by a server request. Any Node program can take advantage of the event loop, as we'll see in the next example. Sometimes it's useful to skip an iteration of the event loop before executing some code. Going back to an example from the last section, we triggered a ready event from a module after a delay. If we didn't implement a delay, the ready event would fire before the script importing the module has had enough time to bind to the event. To remedy this, we can use process.nextTick to defer the firing of our event emitter until after the next time the event loop runs. Another scenario for using nextTick might be to enhance responsiveness by prioritizing execution. For example, deferring the cleanup of temporary files until after responding back to a client. As we saw in this screencast, the event loop ensures that requests to our Node server are handled as efficiently as possible without relying so much on threads. We also learn how to defer execution of code to the next iteration of the event loop using process.nextTick. In the next screencast, we'll learn a bit more about the benefits of asynchronous programming as an alternative to multi-threaded programming. In the last screencast, we learned how the event loop processes incoming requests and dispatches events generated by those requests. We also noted that callback functions enable Node to achieve concurrency without requiring a thread for every request. In this screencast, we'll learn more about asynchronous programming and contrast it with multi-threaded programming. In order to understand asynchronous programming, it is first necessary to understand callback functions. In JavaScript, functions are objects that can be passed as arguments to other functions. In this way, the function passed into another function can be executed or called back when processing is complete. Let's illustrate this with an example. In this file, we have a simple Fibonacci algorithm that accepts a callback function as its second argument. When calculation is complete, the supplied callback function will be invoked with the result as a parameter. Inside the callback, we're able to not only report this result, but also the running time of the calculation. As we can see from the output, our calculation executes synchronously. The message calculation complete does not get logged until after fibcalculator returns the result. To see a callback used for asynchronous programming, we'll use Node's built-in file system module. In the first example, we'll read the contents of a file using the synchronous version of the readFile method. Notice that no callbacks are used. We log the result of the readFile sync call directly. As a result, our test message won't display until after the read operation is complete. In the asynchronous version of this example, we pass a callback to the standard version of the readFile method. When we run this version, the I/O operation is no longer blocking, so our test message is logged immediately. The contents of the file are logged asynchronously as soon as the read operation is completed, and readFile triggers our callback via the event loop. There are several advantages to asynchronous programming over multi-threaded programming. Firstly, client-side developers are already familiar with using callbacks for handling DOM events. Secondly, by using the event loop to act as an intermediary between the program and the thread pool used to execute asynchronous operations, Node developers can enjoy the benefits of concurrency without the complexity of directly managing multiple threads, which requires strategies for avoiding deadlocks and competition over shared resources. Finally, systems that create one thread per connection require a lot of resource overhead, from the CPU time used for context switching to the memory required for an execution stack. In this screencast, we've seen how callbacks work in JavaScript and learned how they can be utilized for event-driven, non-blocking I/O. In the next screencast, we'll familiarize ourselves with Node's conventions for using callbacks. In the last screencast, we learned how to pass a function to another function so that it can be triggered as a callback. In this screencast, we'll cover some of the key patterns for using callbacks. Due to the asynchronous nature of many modules, callbacks are quite common in Node. Since they are passed around with such frequency, it's important to go with the grain by following established conventions. If we revisit the read file example from the last screencast, we can identify several conventions that will soon become very familiar. First, you'll notice that our callback to the read file method is the last parameter in the method call. You should follow the same convention if you create a module with a method that accepts callbacks. Next, we can find another pattern in the parameters passed to our callback. The first parameter is an error object, and the second parameter is the result. There's no strict enforcement for this implementation, but following the convention ensures that any developer can reliably check the first parameter to detect errors. If there is an error, we should handle it and then return from the function. If you are returning an error from your own module, then be sure to pass it as an object rather than a string. If the read file method completed successfully, then the error parameter will be set to null. This is also by convention, so that the error parameter will evaluate to falsy on success. You should avoid throwing errors in functions that are asynchronous, since they won't get caught. Instead, you should pass the error to the callback. However, if you're calling a function that is synchronous, make sure to catch its errors. In this case, we catch a JSON parse error and pass it to the callback. When an unexpected exception does occur, it helps to name your functions rather than defining them anonymously. If we run this example, it will be difficult to locate our error in the stack trace. Naming the anonymous function will give us more context. Since callbacks are used so pervasively in Node, a common pitfall is that you end up with a series of callbacks nested within each other. Deeply nested callbacks can make code difficult to read and harder to organize. As you can see in this example, we have several nested callbacks. One to check for a file, another to read a file, and finally one to write a file. To make things clearer, we can break up the process into multiple functions, passing a callback to each. This may result in a bit more code, but the steps are more obvious, and we'll be able to locate errors in a stack trace more easily. For more advanced control flow optimizations, you can use a utility module such as async.js. In this screencast, we covered some of the conventions adopted by the Node community for working with callbacks. Following these standard practices will make sure that your code plays well with others. It'll be easier to read and debug too. In the next screencast, we'll conclude this section about events by digging deeper into Node's event emitters. So far in this section, we learned about the event loop and asynchronous programming with callbacks. In the final screencast about events, we'll take a closer look at the event emitter, an object that facilitates communication between objects in Node. Indeed, sending and receiving events are so much a part of the fabric of Node that most core modules subclass from the event emitter. To emit an event simply means to signal that a condition has occurred. You can then listen for that event and either take action based on the type or do something with the data passed to the callback triggered by the event. This is a common pattern in event-driven programming. We've already seen event emitter in action in the last section. In video 2.1, we used it to create a module that emits a ready event to signal that it is finished initializing. In a new example, we'll do a little bit more with the event emitter. First, we'll create a module to emit events. We'll start by declaring an object that we'll use to subclass the event emitter object. Next, we'll add some functions that will emit events. Notice that the drop event also sends a message. Finally, we assign an instance of our object to module.exports. In our listener script, we can observe the start event for our object by passing a callback to the addListener method inherited from event emitter. Alternatively, we can use the shorter on method as we do for the drop event. As you can see in the listener for the drop event, the message sent from the emitter object will be accessible as an argument to our callback function. Also notice that we're able to stop observing an event by calling the removeListener method and passing the name of the event and our event handler as arguments. By running this script, we can verify that the events are being triggered and received as expected. As a final note about events, most implementations of the event emitter will generate an error event when exceptions occur. You should always listen for the error event so it can be handled accordingly. Otherwise, the event will be thrown down the stack as an unhandled exception. In this section, we learned a lot about events, from the event loop to event emitters. Callback functions are an indispensable tool for passing messages between objects, and we'll be using them throughout the course. In some of the examples in this section, we also got a preview of the file system module. In the next section, we'll take a more thorough look at working with file streams. In the last section, we did some basic I/O to demonstrate how asynchronous callbacks are used. In this section, we'll discover that the file system module is capable of much more than reading and writing files. To start things off, we'll focus on techniques for working with the file system in Node, from transforming paths to managing files. To facilitate interaction with the file system, Node has a distinct module for handling paths. The path module doesn't actually interact with the file system. It's simply a string utility for path manipulation and resolution. Since the file system separator can vary based on platform, you can reference the character for the current system using the set property. You might use this property to generate an array of all the folders in the path for the current working directory. If you have a path that may contain dots or double system separators, the path module can normalize it for you. Using the join method, you can combine parts of a path together into a complete normalized string. Whereas the join method merely merges path fragments, the resolve method will use the path fragments to simulate path traversal. In other words, it will take your parameters in left to right order and use them to navigate from one location to another as if you were using the cd or change directory command. There are a variety of ways to extract parts of a path. You can find the directory name of a path using the dir_name method. You can also get the base name for a file path with the basename method. If your file has an extension, you can extract that too, using the xname method. By passing an extension string as the second parameter to the basename method, you can get just the file name. Now that we know how to manipulate paths, let's find out how to get information about files and directories. For that, we'll need to use the stat method of the file system module. To get stats for a resource, pass its path to the stat method along with a callback. In the callback, the second parameter will be a stats object. This object will have methods to determine the file type, such as is directory or is file. The stats file also contains properties such as the date of the last modification or the size of the resource in bytes. You can format the full list of properties using the inspect method of the util module. The file system module has other methods available for managing files and directories. We can easily find out if a resource is present in the file system by using the exist method. As usual, the result is returned to our callback. By using the readdir method, we can get an array of file names in a directory. The file system module also has methods for directory management. We can create directories, rename them, and also delete them. There are a wealth of other commands available for advanced tasks, such as creating symlinks, changing file permissions, etc. As an alternative to readdir for listing resources on your system, you may want to try the glob module. With glob, you can match files and directories using Unix shell-style wildcard patterns. To demonstrate, we can modify the last example to list all the PNG files in the image directory. In this screencast, we covered some fundamental techniques for working with the file system in Node. We learned how to manipulate paths and find out information about files using the stat method. Finally, we reviewed other essential methods built into the file system module for managing files and directories. In the next screencast, we'll tackle a couple of different approaches to file I/O. In the last screencast, we became familiar with some of Node's utility functions for working with the file system. With that foundation in place, we're ready to start reading data from files and writing data to them. This screencast will take a look at two approaches to file I/O. We got a preview of file I/O in the last section with our example about nested callbacks. We read some text data from a file, converted it to JSON, and wrote the resulting data structure to another file. In both cases, we passed a callback function that would be triggered after the entire read or write operation completed. Notice that we also pass an options object to set the encoding type. The other possible encoding types are ASCII and base64. There are synchronous versions of I/O methods available that might be appropriate for some tasks, such as reading a configuration file when initializing an app. However, in general, using the asynchronous version is highly encouraged. Using read file and write file is convenient, but it has some drawbacks. When using the read file method, the file will be completely buffered in memory before the result gets returned. If the file is very large, this could result in a lot of memory being allocated. What's more, if an error occurs, you won't be able to cancel the operation once it's started. For reading or writing a file in parts, Node has another set of methods, fs.read and fs.write. These two methods rely on a buffer object for handling data. So far, we've used global objects for process.nextTick and console.log. Buffer is a global class that can be used to store raw data from binary streams. It's not necessary to require a module to use a buffer. When creating a buffer, simply instantiate a global class, passing in the buffer size in bytes. Before we can do any reading or writing, we need to get a file descriptor for the file. This is done with the open method, to which we pass the path of the file that we want to open. We also pass it a flag representing the way we want to open it. If we only plan to read from the file, then we can use the R flag. Once we have the file descriptor, we can then pass it to the read method. We also pass a buffer to store each chunk of data. Since each call to the read method will only return a single data chunk, we must wrap the call with our own read chunk function so that it can be called iteratively. As soon as we detect a chunk that is not equal to the buffer size, we know that we're at the end of the file. At that point, we can close the file and log the accumulated data. We can take the same iterative approach to writing to a file, but this time we open the file with the W flag so that the file will be created if it doesn't exist. We also pass an additional mode parameter to set the permissions of the file if created. Once the file is open for writing, we can pass the file descriptor to the write method. We also pass a buffer containing the data to insert into the file. When we have no more data to write, we can close the file. As a tip for debugging I/O errors, in addition to logging the error returned by the open method, you can also generate a stack trace to help pinpoint the location of the error. In this case, we've triggered an error by trying to open a file without read permissions. In this screencast, we took a closer look at I/O with files. In the process, we learned that it's not only possible to read and write a file all at once, but also in parts. Now that we've covered file I/O, in the next screencast, we'll tackle reading and writing data streams. In the previous screencast, we learned a couple techniques for reading and writing files. One approach used fully buffered methods, while another used partially buffered methods. Node also provides an abstraction for partially buffered data access in the form of readable and writable streams. In this screencast, we'll discuss what makes streams different and how they can be utilized for network application development. Unlike the I/O methods from the last screencast, streams emit events. Streams also allow you to plug the output of one stream into the input of another. Since streams are a common design pattern in Node, tapping into and piping data flows in your app can be very easy. Node introduced some major changes in the Streams API in release 0.10. This screencast will focus on Streams2, the latest version of the API. If you are using a previous version of Node, be sure to read the compatibility notes on the website. Many objects in Node are streams, from HTTP requests to sockets. For the sake of comparison, we'll start with an example reading from a file stream. It may look similar to the script from the last screencast for reading a file in parts. However, it wasn't always this way. With Streams2, we're now required to actively pull data from the flow rather than passively receiving it via data events. To create a stream from our file, we use the createReadStream method from the file system module. By listening for the readable event, we can be notified when the file is ready for reading. As with the partially buffered example from the last screencast, the read method of the stream object must be called iteratively. Rather than passing the buffer in a callback, the read method will return the buffer directly. When the read method returns null, we know that we're done reading the file. At that point, the end event will be fired. Next, let's look at writing to a stream. In this case, we use the createWriteStream method, passing it the path to our output file and an options object. Writing to a file is fairly straightforward. We simply pass a buffer to the write method, along with a callback to be fired when the write operation is completed. When we're done writing all our data to the file, we call the end method on the writable stream. This will cause the finish event to be fired. Now that we've seen how file streams work, let's look at an example for another type of stream that is particularly special, standard I/O. At first glance, this code should look quite familiar. Thanks to the consistency of the streaming API, working with different types of streams should be predictable and relatively effortless. As you can see, we set the encoding of standard in to UTF-8 and then read from it like any other stream. As we read each chunk of data from the input stream, we immediately pass it to the write method of standard out. Streams are a powerful feature in Node and more important than ever given their recent overhaul. We'll be putting them to good use elsewhere in this course, starting with the next section in which we handle flows of network data. In the previous sections, we learned about key features of the Node framework, from creating and loading modules to reading and writing streams. In this section, we'll learn how to apply those features to network application development. We'll get started by building a web server to handle uploaded image files. Even though it's likely that you'll decide to build your network application on top of an abstraction, such as Connect or Express, it's helpful to know what's under the hood. We'll start as we did in previous examples by loading the HTTP module and creating a web server that will listen to port 8000. In our callback, we'll have access to the HTTP request and response objects. From the request object, we can find out the URL that was requested, as well as the request method. This information will be used to route the client request. In this case, we've defined a custom router module to map a handler function to specific combinations of HTTP method and URL. Our router exposes two objects, one for each of the allowed HTTP methods. Within these objects, we define our routes by using the URL as a key and the handler function as the value. If a request is made using an unhandled method or an unrecognized route, then we will return a page not found response. Before we write the response body, we send a header with a 404 status code and a content type of text HTML. In the index route, we generate a successful response by sending a header with a status code of 200 and ending the response with some HTML as a response body. If we start our app and load the root path of our server in a browser, we can see that our page displays with an upload form. Finally, by looping through all the request headers and logging them to the console, we can get more detailed information about the request. Going back to the HTML for our upload form, we can see that the form will submit its data using the post method. We can also find out where the form will post based on the action attribute. In order to handle that post request in our app, we provide a route for the specific combination of URL and request method. Since the upload route deals with files, our router needs to import core modules such as path and file system. We also import the formidable module for parsing data uploaded from the form on the index page. Whenever we receive a post request to the upload URL, we'll use formidable to create a new incoming form. Using this object, we'll set the destination directory for uploads and then assign a couple event handlers. One listener will push files to an array as they get parsed. The other will trigger a function to process all the uploaded files once parsing is complete. Finally, we parse the request. If we detect that one of the files is not an image or that it has already been uploaded, we delete the temporary file created by Formidable. Otherwise, we'll rename the file based on the file name uploaded by the user. Once all the files have been processed, we'll redirect the client to the gallery page by writing a location header with a status code of 302. For now, our gallery page simply writes out a list of the uploaded file names. In this screencast, we got to use some of the fundamental tools for building a network application in Node. We built a web server capable of routing GET and POST requests. We inspected request headers and learned how to write different types of response headers. Ultimately, we created an app that enables users to upload image files. Unfortunately, our image gallery doesn't display any images yet. In the next screencast, we'll learn how not only to serve static files, but also parse data from the URL. In the last screencast, we got our feet wet with HTTP by building a web server to handle both GET and POST requests. We built the server to support image file uploads, but we have no way of showing those images. In this screencast, we'll learn how to serve static files and leverage the URL query string to paginate through the list of uploaded images. In order to get our app to serve static files, we need to set up an additional route to handle those requests. We can detect image files by doing pattern matching on the uploaded file name. Let's see how this would look in our app file. In the updated version, we import the URL module to help us manipulate the request URL, similar to the way we use the path module to manipulate file system paths. As a first step, we grab the path name of the requested page, which is the part of the URL between the hostname and the query string. Request to a path may or may not end in a slash, so we normalize the path name by removing the trailing slash if detected. Next, we look for file extension patterns in the file name to ensure that our app only routes requests for supported image types. If we get a match, then we handle the request with a route exclusively for static files. To simplify our router and keep our code organized, we'll define each route in its own module. In the file for our static route, we normalize the request URL so that it can be referenced on the file system, relative to the location of our app module. We start by confirming that the file exists and respond with a 404 if it doesn't. If the requested resource happens to be a directory or a non-image file, then we return a 403 forbidden error. Otherwise, we use readFile to load the contents of the file. Before writing the file data to the response, we need to send a header that will tell the client what type of content we're sending. To do that, we use the Node MIME module to automatically detect the content type of the file based on the file name. With a small modification to our gallery module, we can generate image tags that reference each uploaded image file. If we start the server and visit the gallery page, we can now see what all those uploaded images look like. This is great, but the page will take longer and longer to load the more images get uploaded. Fortunately, we can use the query string to split up the results across multiple page requests. Let's look at another version of our gallery module that supports pagination. In this version, we import the URL module so we can parse the page parameter out of the URL query string. If the page value doesn't exist or is not a number, then we default to the first page. In this example, we've configured our pagination system to load 5 images per page. To ensure that we don't get other types of files mixed up with our images, we push only the image files to a new array. Then, to control which images get displayed, we use the page size and requested page value to generate HTML for only the currently viewable portion of the files. At the top of our listing, we can generate links that will enable the user to navigate backwards and forwards in the list. These links simply load the gallery with a page value in the query string that is either incremented or decremented. In this screencast, we made some great improvements to our web server. We added support for static files and incorporated navigation by parsing the query string. In the next screencast, we'll cover performance tuning techniques. And we'll finally see what the other half of a network transaction looks like by building a simple HTTP client. Throughout this section, we've been learning how to use Node's core HTTP module to load content. In the last screencast, we modified our web application to serve image files.
In this screencast, we'll look at some ways to improve performance by caching and compressing those files. To complete our coverage of the HTTP module, we'll complement our server example with a basic web client. There are many optimizations we can make to improve the performance of our web server. For our gallery app, we'll modify our static module to set an expiration time for content and compress the data before sending it to the client. As it stands now, our static module only sets the content type header. By adding additional headers, we can prevent clients from making subsequent requests for the same resource if it hasn't been modified. To do that, we first need to set a last modified header to indicate the time of the most recent modification. After that, we set 2 additional headers to determine how long to cache the file. In this case, the time period is 7 days. Although modern browsers all use cache control headers, it's worth sending expire headers too, just in case there's an old proxy in front of the browser. For the cache control header, we specify that amount of time in seconds. For the expires header, we set the value to a timestamp for 7 days in the future. For data compression, we'll use the zlib module that comes with Node. Once we detect that the stream is readable, we'll search the request headers for the encoding method and compress the data if it's supported by the client. Otherwise, we just pipe the data to the client. Pipe manages what's called backpressure, a performance issue caused by a fast read stream on the server that overwhelms a slow client that can't keep up. If we enable compression and reload the gallery page, we can see that the actual payload to the client has been reduced compared to the original data size. For simpler and more maintainable code, consider delegating compression duties to a reverse proxy such as Nginx or LightPD. So far in this section, we focused on the server side of HTTP. For the final example, we'll take a look at building a web client that will send a GET request to pastebin for a snippet of JSON representing a list of colors. To do this, we pass the hostname and the path of the URL to the GET method, and in the callback, set the encoding type for the response and assign event listeners. When all the data has been read, we parse the JSON and iterate over the array of colors. On each iteration, we can use the ANSI module to change the terminal text color for standard out every time we log the name of each color to the console. The HTTP module is a cornerstone of network application development in Node. As we've seen in this section, you can accomplish a lot with it very quickly, but it still takes effort to manage so many low-level details. As we'll see in the next section, middleware like Connect can abstract away these details and make common networking tasks much more convenient and productive. In the last section, we created a server from scratch using Node's built-in HTTP module. We managed to build a static server capable of file uploads, but we spent a lot of time tending to low-level implementation details. In this section, we'll see that middleware like Connect can do much of this heavy lifting for us. For our first example, we'll use Connect to define our own middleware component for a server that sends a variety of responses based on request type. To start using the Connect framework, we first need to install it with npm. The advantage of using Connect is that it provides an abstraction for many server functions such as logging, working with cookies, authentication, and much more. Version 2.7.6 of the Connect framework is used throughout this section. The examples highlight some key features, but Connect provides a variety of middleware for additional functionality, from serving directory listings to parsing JSON. This functionality can be added to our app by importing the framework, creating a server, and passing a middleware component to the use method. As you can see, we can add these components to the server in a chained fashion. The flow of execution will pass from one component to another. This pattern of stacking middleware promotes reusability and makes it easy to bolt on different functionality to your app. To see this in action, let's implement our own middleware for parsing request headers. This custom component returns a function that takes the request and response objects as parameters, plus a next function as a final parameter. In this callback, we'll detect the content types accepted by the client
and store that information in the request object. Finally, we'll make sure control flow continues to subsequent components by calling the next method. In this case, the next component in line is our custom router. In our router file, we route all requests for the route path to our index route module. Otherwise, we set the status code of the response to 404 and pass an error object to the next function. By using the error handler component and setting a name for our app, we can easily display a friendly error page. In the module for our index route, we can write different responses depending on the type of the request that we receive. If the client accepts HTML, we'll send some markup. If it accepts JSON, then we'll send an object. Otherwise, we'll just send plain text. By making a request from a browser, we can see the HTML response. If we use curl to make the request, we can see the plain text version. If we set a header to accept JSON, we'll get an object instead. If we add the logger component, Connect will log information about every request to the console. We're using a filter named short to format this data to only a handful of key points. In addition to built-in filters, you can pass a custom format string to include only the data points you need. We can also use Connect to serve a favicon file. Browsers automatically request this file to visually represent your app in the Browsers tab. As long as we specify the path, Connect will take care of everything else. In this screencast, we learn how to accelerate our development workflow by putting our app together with the Connect middleware framework. We discovered that Connect can handle common tasks for us, such as logging requests and handling errors. We also used it to run our own middleware to parse headers and route requests. In the next screencast, we'll refactor our static server from the last section to take advantage of other conveniences offered by the Connect framework. In the last screencast, we used Connect to serve JSON, HTML, or plain text, depending on the content type accepted by the client. We also got introduced to the utilities bundled with Connect that can take care of tasks like logging and serving a favicon. In this screencast, we'll learn how to use Connect to simplify our static server from the last section. In this new example, our app file is using some of the same middleware from the previous example. At this point, it's worth noting that Connect supports two kinds of middleware, filters and providers. An example of a filter would be the logger middleware. As a filter, it is situated in the middle of the traffic flow. It processes the incoming data, but does not actually send a response. On the other hand, the static middleware acts as a provider. It is an endpoint for the request flow because it results in a response being sent to the client. To configure the component to serve static files, we specify the path for our static assets, which in this example will be /public. Notice that we prefix this path with dir name instead of process.cwd. This ensures that we refer to the location of the script itself, rather than the location where the script was executed, which may be different if we're running the server using a daemon, for example. To serve our images from our new static directory, we simply need to move our image directory under public. Since the path to our images has changed, we also need to update the path that we passed to redir in our gallery module. Our refactored app is also configured to use Connect to manage uploads. All we need to do is set up our app to use the multipart component and pass in an options object to specify the upload path. In this case, it's the image directory in our static folder. Let's look at how the updated upload module works. Since Connect wraps a formidable object, we will automatically have access to the uploaded files as the files property of the request object. We just need to reference the files based on the name of the field that was submitted. Now we don't have to worry about parsing the form or assigning event handlers. Once the post method of our module gets invoked, we can immediately handle the uploaded files. If you plan on using middleware like multipart and body parser for file uploads, Bear in mind that the temp files created for uploaded files are not automatically deleted. Fortunately, you can run the reap utility as a cron job to manage the cleanup of these files. As a final refactoring step, we've added the query component for parsing query string parameters. This will result in a query property being added to the request object. This means that in our gallery route, rather than importing the URL module, we'll be able to reference this data directly. We can also reuse our error handler to present the user with a friendly error page if they try to browse out of range or an exception occurs. In this screencast, we revisited our static server example from the last section and refactored it to use the Connect framework. We were able to achieve the same results using less code by taking advantage of plug-and-play middleware components. In the next screencast, we'll take a quick look at how to use middleware to tune our server's performance. In the previous screencast, we rebuilt our original static server example using the Connect framework. From handling file uploads to parsing the query string, Connect provides us with many middleware components to speed up network application development. In this screencast, we'll look at Connect's middleware options for performance optimization. Our first static server, built with the HTTP module, required that we import the zlib module in order to compress image files. If we use Connect, all we have to do is run the compress middleware before we add the static middleware to our app. By default, the component is configured to run compression for text, JavaScript, and JSON files. We can override that behavior by supplying our own filter, which in this case will only apply to image files. If we force refresh the gallery page, we can verify that we're serving compressed versions of the files. Setting cache control headers using Connect is also a breeze. To set a cache period, all we have to do is set the max age option for the static middleware. The option value must be a number in milliseconds. We'll configure it so that the client will cache the images for 4 days. By inspecting the response headers for one of our images in the browser, we can confirm that the cache control header has been set as expected. For caching on the server, Connect also offers a component called static cache that acts as a memory cache layer on top of the static middleware. However, static cache has been deprecated and will be removed in version 3.0 of the framework. As an alternative, you can configure a web accelerator like Varnish to sit in front of your application as a caching reverse proxy. Although it won't improve performance directly, we can further optimize our app by setting a file size limit for image uploads. To accomplish this, we just need to use Connect's limit middleware, passing in the desired file limit. This value can be either a number in bytes or a string representation using KB, MB, GB, and so forth. If we try to upload a file that's larger than our limit, we can verify that an error gets displayed. As we've seen in this screencast, the Connect framework not only makes it easier to build our application, but also provides tools for improving server performance. But Connect is only the tip of the iceberg. In the next section, we'll discover that we can delegate complex web application tasks to an even higher level framework like Express. In the last section, we found out that the development process can be greatly simplified by using Connect as a middleware framework. Although Connect offers a solid structural foundation, it lacks a comprehensive abstraction for a variety of web application features. In this section, we'll get acquainted with Express, a framework built on top of Connect that streamlines many aspects of web app development. In this screencast, we'll use Express to generate a skeleton app and then configure a simple app of our own. Express follows in the footsteps of other frameworks such as Ruby on Rails and Cake PHP that simplify the creation of HTTP applications. Based on Connect's middleware engine, the Express framework is an integrated solution that provides scaffolding for rapid development and boasts a more complete collection of middleware components. At the time of this recording, the latest version of Express is 3.4. As with the Connect framework, we can install Express as part of a pre-existing app. However, Express also comes bundled with an executable to generate a skeleton app for us. To use this tool anywhere on your system, install Express globally with npm. For convenience, you can use the npm shortcut I in place of install. Once installed, we can call the Express executable to generate the boilerplate code and folder structure for a simple app.
Invoking the command with options will automatically configure your app to use selected middleware. Possible options include session support, template engine, CSS preprocessor, and more. Let's look at the output of the command to get a preview of what a full Express app looks like. We can find the standard app.js and package.json files. There's already a public folder, which has been configured to act as our static directory. Finally, we have a routes folder and a views folder for putting our HTML templates. We'll learn more about views and templates in the next section. In this screencast, we'll create an app from scratch that supports serving static files and basic routing capabilities. We'll begin by creating a package.json file in our app directory. All we need right now is to list Express as a dependency. It's recommended to use a specific version to avoid unexpected issues with future versions. Before proceeding, let's install the dependency. Next, we'll create the app.js file. To get started, all we need is the Express module and the HTTP module. We create our Express app and pass it to the HTTP module to create the server. Notice that we also set a property on our app for the port that we want to use. In this case, we assign the property based on an environment variable, if available. Otherwise, the value will default to port 3000. We can test our app by starting the server in the usual manner, but this time we'll pass an environment variable to use a custom port. When we run the server, we can verify that port 8000 appears in our log message. Now let's get ready to set up our app to route requests and serve static files. First, we'll create the necessary folders. Then, we'll add a favicon file to the static folder and create an index file inside the routes folder. Back in our app file, we'll import the routes folder and configure our app to use the router middleware. Now all that's left is to define a route for GET requests to the home page. In this case, we'll direct users to the index route inside our routes module. For now, this route sends a simple HTML message. Since Express augments the response object, we can use a higher level method called res.send to automatically send headers before writing the response. Let's wrap up by configuring our app to serve the favicon file. This requires us to configure the favicon middleware with a path to the file. We also pass an optional settings object to cache it for 30 days. Finally, we need to configure Express to use the static middleware to serve files in our public directory. This is a common location for static assets like images, style sheets, JavaScripts, etc. The order here is important. Make sure you add the static middleware before defining any routes. Before we test our changes, let's make a quick update to our package.json file. To make it easier to start our server, we'll add a scripts object with a start property. This is the command that will be executed if we call npm start in our project directory. In this way, we can automatically launch our server with a custom port every time. Browsing to our server, we can verify that Express is routing requests for the homepage and the favicon file is being served by the static middleware. In this screencast, we got a taste of what Express can offer as a web application framework. Building upon the Connect middleware engine, Express provides a much more integrated solution for developing HTTP applications. In the next screencast, we'll look at how to save state during a user's visit by storing session data. In the last screencast, we learned how to use Express to generate a skeleton app and started building the foundation for a to-do app in Express from scratch. In this screencast, we'll learn how to persist data in our task list by integrating the Express session middleware. Sessions are obviously not a long-term data storage solution, but it's enough to get our initial prototype up and running. Express comes with a built-in solution for storing sessions. When we generated our app, we could have included a sessions flag to include session support. Since we're going to continue building onto our existing to-do app, we will manually add the lines that Express would have created for us. As we can see, there are only 2 lines of code required, somewhere before we define our routes. One for the cookie parser middleware, and another for the session middleware itself. By passing a secret string to the session middleware, we can enable signed cookie support to prevent anyone from tampering with the data stored in the cookie. If you enable sessions using the generator, Express will default the secret to a placeholder value. For additional security, you should replace this with a randomized string of numbers and letters. A site like random.org can create one for you. With the middleware in place, we can now access sessions via the request object. To demonstrate, we'll add some logic to display a dynamic welcome message to the user based on whether they visited the site before. On the first visit, we'll show a default welcome message. On subsequent visits, we'll show a custom message welcoming the user back to the site.
Unfortunately, saving session state with memory store will leak memory and will be confined to a single process. This may be fine while developing our app, but in production we should use an external data store. As an alternative, we can use a key value store such as Redis. Although we'll take a deeper look at databases in a future section, we'll get a head start now by installing Redis. This involves downloading the binary and installing it. Once Redis is installed, we can then install the Connect Redis module. By running npm install with a save option, we can add it as a dependency to our app at the same time.
To use the external data store, we'll need to import and execute the Connect Redis module, passing it the Express object. To customize our session middleware to use the new store, we set the store option to a new instance of Redis store. If you need to configure Redis store with your own database options, here's how that would look. We can also configure a max age option for our session component to expire the session after an extended period of inactivity. Sessions are an essential tool for maintaining state within an app. Frequently, it's also necessary to associate sessions with specific users. Although this topic is beyond the scope of this screencast, Passport is an excellent example of authentication middleware for Express. In addition to a local strategy for username and password, it also supports a variety of third-party authentication strategies, including OAuth, Facebook, Twitter, Google, and more.
In this screencast, we learned about persisting application state using session middleware built into Express. For development purposes, we initially saved session data with cookies. For a more robust solution, we then refactored our implementation to use Redis as an external data store. Now that we're ready to store information in a session, in the next screencast, we'll wrap up our to-do app prototype by integrating the actual task management functionality. In the last screencast, we integrated session storage into our app so that we can add to a running list of to-do items. In this screencast, we'll pull everything together by incorporating a form that will add new tasks to the list. For each new item, we'll modify the stored session and display the updated list. In order to start adding to-dos, we need to add a form for capturing data from the user. To keep things simple, we'll add this form to the home page. When submitted, it's configured to post to a save route, which hasn't been created yet. The form itself contains a label, a text field, and a submit button. To wire things up, we'll need to add a new route to handle form submission. This route will be able to load the value for the submitted to-do item by accessing the matching key for the field name within the request body object. If this value exists, we'll store it in the session within a to-dos array. Finally, we'll redirect back to the index route. In order to access the body property of the request object, we'll need to add new middleware to our app. The easiest way is to add the body parser middleware. As stated in the documentation, body parser is just a wrapper for the JSON, URL encoded, and multipart middleware. Since our form doesn't need to handle uploads, it's better to only use the middleware we actually need. In this case, our app only requires the URL encoded middleware. In the index route, we'll look for the to-dos array within the session object. If it exists, we'll loop through all the tasks and add them as list items in an unordered list. To integrate the to-dos form, we'll need to import the new store route into our app and make sure that only post requests get routed to it. Before starting the server, we first need to start up Redis. We can do that by running Redis server. Now we're ready to start our app. In this screencast, we completed the prototype for our first app using the Express Web Application Framework. We added a form to the home page and used the URL encoded middleware to process data submitted to our new route. Using session middleware from the last screencast, we were able to store values in an array and display them as they get added. In the next screencast, we'll learn how to use Express for logging and handling errors. In the last screencast, we completed a simple to-do app with Express. In its current state, our app doesn't have any special error handling and only logs output to the console. In this screencast, we'll learn about utilities for handling errors thrown by our app and logging output from our server into files. Maintaining an access log with Express is easy. To do this, we can use the logger middleware we first used for our Connect server in the last section. Continuing with our example to-do app, let's add some code that will append information about requests to an access log. In order to do this, we need to import the file system module and create a writable file stream. This file will be created if it doesn't exist, and anything written to it will be appended. In order to log this file, all we have to do is pass an options object to the logger middleware with the desired format type and a reference to our writable stream. To test, let's create our log directory and start the server. Even though we make requests to the app, no messages will appear in the console. If we output the contents of the access log file, we'll see that the access data has been stored there instead. We could go a step further and redirect any console logs to an output file. To accomplish this, we can install a module called Forever. In addition to managing our server logs, this utility will monitor our server and automatically restart it when it crashes. Since we'll be using it as a command in our system, let's install it globally. Now that Forever is installed, let's modify the start command in package.json to use Forever. By using the -o option, we can output any console log messages to a destination log file. Since we're now using Forever to start our app, it only makes sense to add another command to stop our server using it too. Now when we run npm start, we can see that our server is launched in the background with Forever, and we no longer see the log message about listening to port 8000. By running npm stop, we can shut down the server. If we check output.log, we can confirm that our console log messages are streaming to it. For handling errors in Express, we'll take different approaches based on environment. For the moment, we'll configure our app to use the error handler middleware when in dev mode, which is the default environment. It's important to note that the error handler must be configured before any routes are defined. We can customize the error handler by setting the title of our app. If we throw an arbitrary error from the home page and load it in the browser, we'll see a developer-friendly error page with a status code and a stack trace. This is useful while developing an app, but in a production environment, we should log errors and present a more user-friendly error page. To use our app in production mode, all we have to do is set the node.env variable in our script start command. In order to catch errors in our app, we can write our own middleware for handling exceptions. Let's make a lib directory and create a new file in it called errorhandlers.js. In order to write the HTML for our custom error pages, this middleware will import a new error route. Our error middleware will export several different components. The PageNotFound handler will set the response status to 404 and load the error page for any unhandled route. The error handler will act as a catch-all handler, setting the status code to 500 and passing the error message to the error page. The last component will log every error and pass the error on to next. To integrate this new middleware, we first need to import errorhandlers.js into our app file. We also need to set up our app to use each of the components towards the end of the file. Note that order here matters. The error handlers must go at the end after PageNotFound handler. As a final step, let's add another parameter to the start script so that stack traces will get written to an error log file. Now if we try to navigate to an unknown URL, we'll be presented with the user-friendly 404 page. In addition, if we revisit our intentionally broken home page, we'll see our custom error page. And if we look at the error log, we can see that the stack trace was stored. In this screencast, we learned how Express can help us perform common server tasks. We started by configuring logger middleware to write request metadata to a writable stream. We also utilized Forever to automatically log errors and console output. Finally, we generated user-friendly error pages by creating our own middleware for handling errors. In the next section, we'll focus on refactoring the presentation layer as we learn about taking advantage of templates to render views. In the last section, we created a to-do app with Express. Much of the construction was focused on server functionality such as routing requests and storing data in a session. In this section, we'll cover view templates, an essential front-end development feature integrated into the Express framework. In this screencast, we'll discuss considerations for selecting a template engine. Templates aren't strictly necessary for an Express app, but they serve an important role by enforcing a separation of concerns. In other words, templates help keep our presentation markup from mingling with our business logic. As an added benefit, they can improve application performance since template files can be cached. There are a wealth of template engines available for Node, many of which are compatible with Express. By default, Express uses Jade, an engine inspired by Haml, an HTML abstraction markup language for Ruby. In a nutshell, Jade abstracts the DOM with its own syntax for representing elements, including their attributes and hierarchical structure. This syntactic sugar results in code that is more elegant and easier on the eyes than vanilla HTML. Similar to the way CoffeeScript beautifies JavaScript, Jade beautifies HTML. For the examples in this tutorial, we'll stick to using the EJS template engine since it has a syntax that is more universally recognizable. If you've used Ruby on Rails, EJS uses a syntax similar to Ruby's ERB templates. In both cases, you can display data within markup by adding these special opening and closing tags. Any data between these tags will be inserted into the page. By peppering your markup with these tags, you can dynamically populate your view with content and runtime. In development mode, EJS won't cache your templates. This means that you can make changes to your template code while your server is running and see the changes reflected in the browser. In production, caching will be automatically turned on for EJS templates by Express. The special tags used to populate data into a template will vary depending on the engine that you choose. Engines like Handlebars and Swig use curly braces instead of ERB-style tags. As you can see from this example Swig template, the difference isn't dramatic, but it's a little easier to visually pick out the template expressions from the surrounding HTML. Much of the variation between engines has to do with speed and supported features. If you're just experimenting, then EJS is a convenient place to start because it's already integrated into Express. For comparing template engines at a glance, Paul Armstrong, the creator of Swig, compiled an excellent feature matrix. He's also included a suite of benchmarks for comparing the performance of selected engines. As with most benchmarks, these results should be taken with a grain of salt. Ultimately, your choice will likely depend on your syntax preferences and feature requirements. For additional perspective, the LinkedIn engineering team posted some illuminating results from their template engine shootout. In this screencast, we learned that templates can help us separate the view layer from the rest of the application. We covered some of the syntactic differences between template engines and highlighted a couple resources for comparing features. In the next screencast, we'll start integrating EJS templates into our to-do application. In the previous screencast, we got an introduction to view templates in Express. We compared a few different template engines, but settled on EJS for our to-do app. In this screencast, we'll learn how to use EJS templates for rendering views. As explained in the last section, we skipped creating templates in the initial iteration of our to-do app. By convention, these files are stored inside a views directory. In our app file, we'll configure Express to look for templates in this folder. We also need to set the view engine middleware to EJS. To see templates in action, let's start by refactoring our error route. As it's written now, the error route generates an HTML fragment containing a header tag with the name of our app and a paragraph tag with an error message. Every route should return a fully formed HTML page, so let's recreate this markup inside of a new template file created inside our views directory. In the template, we're able to render a full HTML page, complete with a title tag and a style sheet. The markup itself is cleaner because we no longer have to worry about interpolating variables within the HTML string or escaping new lines. Instead, we just place our variables between the special tags. Now all that's left to do is render the template in the error route. This new code will replace the res.send line we had before. We indicate which template to render by specifying the file name as the first argument. As the second argument, we use an options object to expose our variables to the template. For this to work, we need to match up the variables referenced in our template with their respective keys in the options object. We can test that this worked by starting the server and navigating to a bad URL. Incidentally, EJS can be configured to use custom delimiters for its special tags. As a version 3 of Express, this view option can be configured by using app.locals. Now our error template can be refactored to use the new delimiters. Of course, we should update our index route to render view template too. In this case, we pass into the template an options object with a title, a description, and the HTML for our task list. Looking at the template, we can see that the title and description use the same tags we've been using all along. However, to output the to-dos variable, the opening tag uses a dash instead of the equal sign. This is due to the fact that standard tags escape variable values by default. In order to render our variables as is, we need to use a tag for unescaped buffering. The dash in the closing tag is not required. Adding it will prevent a new line from being automatically inserted after the value. Although our template works fine and we managed to move a lot of HTML into our view, we're still generating some markup in the index route. Fortunately, we can move this code into the template, albeit in a modified form. Instead of passing the generated HTML to our template, we'll pass the to-dos array itself. Inside the template, we can implement conditional logic and loop over the array by using another unbuffered version of the template tags, specifically for executing code. Each time we iterate over the array, we can directly output the variable value from that array item within the appropriate markup. By using an if-else statement, we can ensure that a default message appears when the to-do list is empty. Bear in mind that some engines, such as handlebars, do not support logic within templates. In that case, you'll need to apply the required formatting in the route or in the model. In this screencast, we finally got our hands dirty rendering views. As a result, we were able to clean up our routes by moving HTML markup into separate template files. What's more, we learned how to execute JavaScript within templates in order to generate HTML dynamically. In the next screencast, we'll look at advanced templating features such as using layouts, includes, and variable filters. In the last screencast, we cleaned up our routes by separating presentation-specific code into views. In this screencast, we'll learn about other features available in EJS to further optimize the way we write markup within our Express application. For example, we'll discover how to reuse more HTML code by using layouts and includes. Finally, we'll look into using the filter API for manipulating data in our templates. If we analyze the templates we created in the last screencast for the index page and the error page, we'll notice that there's some redundant markup at the beginning and the end of the files. Instead of only writing content for the body of the page, we're creating the whole page from scratch every time. To fix this, we can use layouts. Unfortunately, the layout feature isn't available by default in version 3 of Express. In order for it to work, we must first install the Express Partials module. Once installed, we will need to import the module into our app to configure it to use partials. When that's ready, we can create a file in the views directory named layout.ejs or layout.jade if you're using that engine. This file will now contain all the wrapper code from our other routes. In order for the content of each view to be populated into the layout, we will need to add an unescaped version of the special tag wherever we want the body of our page to be inserted. The body variable will be automatically set to the content of a view when it gets rendered. The only other change required is to remove the now unnecessary layout code from our views. Includes are another great EJS feature for reusing code inside views. Let's say we wanted to use the same title and description from the index page on multiple pages. We could add that code to the layout, but then we wouldn't have as much control over when it appeared and when it didn't. As an alternative solution, we can add the code to an include file and only add it to the views that need it. To do this, let's create an include file called header.ejs within a new includes directory inside views. To include the file in our index view, we simply need to add special tags within an include command and the path to the file. Notice that the path is relative to the location of the view including the file. You may have noticed that syntax highlighting isn't being applied for our EJS include file in Sublime Text. Luckily, we can remedy this with the Apply Syntax plugin. Once installed, just add a new XML syntax rule for EJS file types in the user settings file. Then update the file. You should now see the syntax highlighting properly applied. Another utility supported by EJS relates to filtering. Filters are intended to be a designer-friendly way to manipulate data within views without having to write additional JavaScript. For example, let's say we wanted to automatically capitalize the first letter of every to-do item. We can accomplish this by adding a colon to the opening tag, and then piping the to-do variable into the capitalized filter. Filters can even be chained together in a sequence. We can confirm that this is working by reloading the browser.
EJS has another great feature we can use to refactor our template. Instead of iterating over each item using for each, we can use the map method to apply a function to each item in the list. We end up with the same amount of code, but now it's a bit more readable. There are a variety of other features and filters available for EJS. You can browse the full list here.
In this screencast, we learned about some of the powerful templating features we can use in our Express app. With layouts and includes, we're able to reuse more code and keep our views as tidy as possible. We also discovered that it's possible to manipulate data and perform calculations directly within our views with the help of filters. Now that we have a deeper understanding of the presentation layer, in the next section, we'll dive into data storage and the model layer.
In the last section, we learned how to manage the presentation layer more efficiently by leveraging templates. At this point in the course, we've stashed data in a session cookie as well as Redis store. In this section, we'll learn how to store data using another popular database called MongoDB. In this screencast, we'll cover installation and setup of a Mongo database. In addition, we'll get acquainted with an object modeling tool for MongoDB called Mongoose. We first used databases in section 7 when we installed Redis for our to-do application. In that app, we use Redis by configuring our session middleware to save data using Redis store. Redis and MongoDB are both examples of NoSQL databases. Whereas relational databases excel at modeling complex data relationships, NoSQL databases are built for scalability and performance. They're designed for large volumes of data that may or may not be structured. In addition, NoSQL databases don't require a predefined schema. This means that data can be inserted without requiring downtime for migrations to a new database schema. Redis is a key value store that provides fast access to a selection of useful data types such as hashes, lists, and sorted sets. Like Memcache, Redis is often used for caching. It's also well suited for applications that demand real-time performance. The downsides are that it is single-threaded and it requires that all data must fit in memory. By contrast, MongoDB is a document store that supports complex data structures, including nested documents. It also uses an ad hoc query language that should be familiar to SQL developers. One of its main benefits is built-in horizontal scalability, with features like auto-sharding and master-slave replication. The easiest way to get started with MongoDB is to install it with a software package manager such as MacPorts, Fink, or Homebrew. To install with Homebrew, simply run brew install MongoDB. This will install the database on your system and automatically generate a config file. The config file will set up the location of your DB as user/local/var/MongoDB. To test that MongoDB is installed, run mongo-version. Mongo is the command line interface for MongoDB. The command to start the Mongo database server is mongod. This will start the database and begin listening for requests on localhost port 27017 by default. To use authentication for database connections, we must first create an admin user. We'll start by running mongod with the auth option to enable authentication and then connect to the admin database. Next, we add an admin user, then switch to the RSVP database for our new example. To confirm that authentication is working, we can test by trying to show the collections of this database. To create a user for the RSVP database, we must first switch back to the admin database and authenticate. If we go back to the RSVP database, we can now access collections and create a new user. By connecting to the RSVP database with this user's credentials, we can verify that we have the right permissions. With MongoDB installed, we're ready to install the Mongoose module. Mongoose is a wrapper for the native MongoDB driver for Node. It enables us to focus on defining schema in its data modeling environment
instead of worrying about interfacing directly with MongoDB. Installing Mongoose can be done with the usual npm install command. We'll install it as a dependency for our boilerplate RSVP project. We can see that it's installed the MongoDB driver module for us. In this screencast, we installed MongoDB and configured it to use authentication. We also got an introduction to a data modeling tool for MongoDB called Mongoose. In the next screencast, we'll get our app to connect to the RSVP database. In the last screencast, we got MongoDB installed and running on our system. We restricted access to our database by creating a new user and running the server in authentication mode. In this screencast, we'll create an interface module for opening a database connection. We'll also make sure that our app can connect to the database with our new user. At this stage, our RSVP application is set up with Mongoose for object data modeling and a handful of modules from our to-do application. Essentially, we have a boilerplate app capable of writing to logs, handling errors, storing session data, and rendering view templates or partials. Our only route is for the home page, which has some basic layout and styling. Before we can do anything useful with our app, we first need to connect to the database. To accomplish this, we'll create an interface to handle connecting to MongoDB. Since we wouldn't want to expose server credentials within our application codebase, we'll start by creating a configuration file with all the necessary options for connecting to a database.
As you can see, it's just a JSON object containing hostname, database name, port number, and login credentials. To use the configuration options in our app, we'll simply require the file. Next, we'll import the database connection interface module.
This module has interface methods for connecting to and disconnecting from a database. These methods will fire callbacks when the connection has been fully opened or closed. The connect method requires a parameter for connection options, which we will provide courtesy of our configuration file. We'll initiate the connection once our server has started up. Whenever the node process for our app exits, we'll close the connection.
Now that we've set up our app to use a database connection, let's look at how the interface works. First and foremost, we import Mongoose, which itself acts as a wrapper for the MongoDB driver. In our connect method, we build a connection string from the options passed into it, using sensible defaults for host, port, and database. If the connection options are missing credentials, we immediately return with an error. Otherwise, we pass the connection string to mongoose.connect. Finally, we get the handle for the database connection and use it to register event handlers. This will ensure that our callback gets triggered in the event of an error or whenever our database connection is ready. We also assign handlers for other events, such as when the database gets connected, disconnected, or reconnected. Note that by default, MongoDB will automatically try to reconnect if it loses its connection. You can override this by setting the auto reconnect configuration flag to false. The disconnect method is straightforward. It simply closes the database connection. Both methods use the connected flag to reference the current connection status.
If we start our app, we can check the output log to confirm that we've connected to the database successfully. If we try restarting the server with bad credentials in our configuration file, we'll see an authentication failure message appear in the error log. In this screencast, we integrated database storage into our app by connecting to MongoDB via Mongoose, our data modeling tool of choice. We encapsulated the details of opening and closing a database connection by creating an interface module along with a configuration file for storing connection options. In the next screencast, we'll define the schema for the event model, the core data object in our RSVP application. In the last screencast, we updated our event RSVP app to connect to MongoDB through an ORM-like library called Mongoose. In this screencast, we'll take advantage of Mongoose's data modeling features by using it to define a schema. In addition, we'll set up validation and create a skeleton REST API for routing actions within our app. A key benefit of using a modeling environment like Mongoose is that it provides a framework for declaring the structure of our data and defining relationships between models. It also offers powerful features for executing queries and validating input. We'll get started by defining a schema for the event object. In Mongoose, every schema maps to a collection in MongoDB. The schema serves as a template for the documents stored in that collection. To follow the MVC or Model View Controller pattern, we'll create our event schema in the Models folder. At the top of our model file, we import the Mongoose module and save a reference to mongoose.schema. We then use that variable to create a new instance of a schema based on a JSON object representing our model. In this case, our model will have two properties, the title of the event and the event date. For each key, we're only required to set the schema type. Valid schema types are string, number, date, buffer, boolean, mixed, object ID, and array. Of course, we can do more than set the schema type, such as designating certain fields as required or ensuring that a value is unique. For this example, we'll set default values for both of our fields. Now that our schema is defined, we can register it as a model. This means that other parts of our code will have access to our model from Mongoose's model method. For convenience, we'll export the model as a property of our module. As mentioned earlier, we can use Mongoose to define validators for our model. These validators can be used to filter values stored in our collection. If a value does not pass the validation requirement, then the save operation will be aborted and a validation error will be raised. For the event model, we'll validate that any dates stored in the app match a regular expression for a UTC formatted date string. We'll also make sure that the event date is in the future by comparing it to the current time. Now that our model is ready, we'll turn to the controller piece of our MVC application. A controller acts as the glue between the model and the view. In web-based architecture, controllers typically respond to user actions by handling requests and triggering changes in the model or the view as a result. For our application, we'll create a single interface for controller logic. This module is loosely modeled after the REST architectural style, meaning that we will attempt to map CRUD actions in the application, that is, create, read, update, delete, to their appropriate HTTP verbs. For now, we'll stub out the methods in our REST API and configure our app to route to these methods based on a combination of a request path and HTTP method. As evidence of the RESTful design pattern, you'll notice that the post method is used for creating a new event, but updating an event uses the put method. All other actions use the HTTP get method, since we're only showing a form, event details, or list of events. For the sake of expediency, we'll also use the get method for destroying events. In an ideal implementation, this type of action would use the corresponding delete verb. A strict RESTful approach would also eliminate verbs like create, update, and destroy from the URLs, but we'll include them in order to simplify the implementation and make the controller mapping more obvious. In this screencast, we made some strides towards storing structured data in our application by defining a schema in Mongoose. This schema is the blueprint for event data we'll be storing as a MongoDB collection. To mediate interactions between the model layer and the view layer, we also built the scaffolding for a RESTful API. In the next screencast, we'll wire everything together so that our app can start adding events to the database. In the last screencast, we laid the groundwork for a web application capable of storing and managing events. We defined an event model and outlined a controller to create, show, modify, and delete events. In this screencast, we'll look at how we might implement each of these controller actions. In order to add events to our app, we'll need a form to enter the title and date of each event. Our event form template is actually very simple, since it acts as a shell for two partials, one that shows validation errors, and another that renders a specific version of the event form, depending on whether the event is being created or updated. The errors that we pass to the template can be used to highlight fields in our form partials that contain bad input. The event creation form uses a post method for the form action, as expected, but the update form uses a post method too. In the previous screencast, we configured our app to use the more RESTful put method for updates. To use put and delete HTTP verbs, we need to do two things. First, we need to add the method override middleware after the URL encoded middleware. Then, to set the desired method, we leave the form action as post
and add a hidden input named _method to the form.
To see how the event gets created, let's look at the create event action of our controller. The action that we perform depends on the HTTP method. If the method is get, we call a helper function that simply renders the form. If it's post, we pass the request body to a different helper that will process the submitted data. Since our update form passes an event ID as a request parameter, our save event helper function looks for that value to determine which action to take. If no ID is detected, then we create a new event using the model that we defined in the last screencast. If an ID is found, then we attempt to find a matching document by calling the mongoose method findById. This will return the result, which we can then modify and save. Mongoose's update method can do this in one step, but unfortunately that approach does not trigger validation. Whether creating or modifying an event, we can detect validation errors and use them to display feedback when we re-render the form. If we try to submit an invalid date, we'll see the error in our log. We can identify the offending field by searching for a matching path in the errors object. If we successfully create an event, we can verify that it gets added to the event list. The controller action to list events calls the mongoose find method to get a result of all the documents in the collection. We pass this collection to the events template that generates links for each event. Each URL will pass the event's unique identifier as a request parameter. For the event link and the event's update link, we'll use this ID to query for a matching record. If there is no match, we'll call the next method to pass the request onto the error handler middleware. Notice that we don't even need to run a Mongoose query if the ID doesn't match a regular expression for a valid MongoDB object ID value.
For our controller's delete action, we use the remove method to take the matching event out of the collection. Again, destroying an event would ideally be done by submitting a form using the delete HTTP method.
In this screencast, we built out most of the functionality for our event RSVP application. With Mongoose, creating a new event in our database is as straightforward as instantiating an object. Mongoose also makes it easy to query a collection for matching documents and either update the result or remove it from the database. In the next screencast, we'll explore how to add subdocuments to our event model to track RSVP responses.
In the last screencast, we developed a web app for managing events as documents in a MongoDB collection. As it stands now, our app is only capable of storing the title and date of events. In this screencast, we'll define an additional schema for RSVP responses and associate it with our event. To keep things simple, our prototype will allow any visitor to respond to any event listed on the site. In order to store RSVP responses, we need to modify our model by adding a new schema. This new schema has one optional field for guest name and two required fields for email and RSVP status. We can use the enum validator for the status field to limit the types of responses to a predefined array of options. Since subdocuments can have their own validators, we'll use another regular expression to validate the email field. We don't need to register our response schema as a model, but we'll export the response schema so that the enum values for status can be accessed in our controller. With that done, all that's left is to define a parent-child relationship between the event schema and the response schema. To accomplish this, we add a new field to our event schema whose value is an array of subdocuments based on the response schema we just defined. Subdocuments are just like regular documents, except that they only get saved when their top-level parent gets saved. Any errors in a subdocument will get bubbled up to the parent and appear in the errors array of the save callback function. In order to start adding responses to an event, we'll need another form to capture the data. This time, we've implemented the form as a dialog. The action for this new form uses a new path, with the event ID as the request parameter. You'll notice that we use the HTTP put method for this form too. To see why, let's take a look at the route for this form action in our app file. Although we're functionally creating a new response, technically we're just updating the parent event. In our controller, the save event helper method called by update event is already being passed the request body. To add the response to the event, we can construct a response object from the submitted values and push it onto responses, a document array associated with the matching event object. Finally, we need to save the parent document in order to save the response and store it in the responses document array for this event. Any validation errors bubbled up from the subdocument can be detected in the error object passed by the parent document to the callback. For response errors, we use the session object to save the error and redirect back to the event page. To show our responses on the event page, we use a getResponses helper method to sort our responses into separate arrays for each response type. We'll pass these arrays to the view that gets rendered by the showEvent controller action. Each object will contain the name of the guest, the response ID, and an image generated from the MD5 hash of the guest's email, thanks to the Gravatar module. In our event template, we can then loop through each of the response types we define in our enum. In a responses template, we can use that status value to loop over all the objects within each of the arrays that we created in the getResponses helper method. To delete a response, we pass two request parameters to the destroy controller action, one for the event ID of the parent and one for the response ID. Once we've found the parent document, we can find the matching response by passing the response ID to the ID method of the responses document array. This will return the matching subdocument as a result, which we can manipulate in the same way as a normal document. In this instance, we delete the response by immediately calling remove. In this screencast, we learn how to add responses to our RSVP application by associating a new schema to the event schema as a subdocument. This enables us to push new responses to a document array for each event. These subdocuments can be updated or removed just like any other document. The only difference is that changes are preserved by saving the parent document. In the next screencast, we'll enhance our RSVP app to update itself in real time using socket.io.
In the last section, we integrated MongoDB for database storage so that our app is able to manage events and RSVP responses. In this section, we'll discover how to trigger visual updates in our app as soon as new documents or subdocuments are added to the MongoDB collection. In this screencast, we'll install Socket.io and configure our server to start listening to socket connections. One of the limitations of HTTP is that it's a stateless protocol. This means that once a server sends a response to the client, the connection is closed and no more data will be sent until the user makes another request. With the advent of AJAX, it's now possible to make asynchronous requests without requiring a page reload. Combined with a long polling technique that keeps a connection open, AJAX can simulate real-time communication. Fortunately, the WebSocket API is now available as a more robust alternative to polling. With WebSockets, you can push messages in both directions between client and server. What's more, WebSockets will work over secure or insecure protocols, and even support messaging across different domains. Socket.io is a library for Node that provides a unified API for both WebSockets and its fallback transports for clients that don't support WebSockets, such as AJAX long polling and FlashSocket. It handles many low-level details and manages implementation differences between clients, making it much easier to develop consistent and reliable real-time features in your app. To get started with Socket.io, we simply run npm install socket.io inside our project. This will install both the server-side and client-side libraries. After importing the library into our app, we then start our HTTP server and attach Socket.io to it. Now we're ready to configure our server to start listening to socket connections. We do this by registering a connection event listener for the sockets manager, io.sockets. This callback will be triggered whenever a client connects to the server. For each socket that gets connected, we assign another callback to be fired when the client disconnects. That completes the server configuration, but for bidirectional communication, the client will require changes too. First, we'll need to include the client-side library for Socket.io to get things working end-to-end.
This can be done by loading the socket.io.js file in our page layout. Once we've loaded the client-side library, we can reference the IO global variable and use it to connect to the server URL. Now, if we start the server and load in a page of our app, we'll see that the socket connection gets logged by our listener. If we navigate away to another site, the disconnect message will be logged as well. In this screencast, we learned that Socket.io provides a common API for implementing bidirectional, real-time communication in our apps. After installing the server-side and client-side libraries for Socket.io, we were able to start listening for activity on socket connections. In the next screencast, we'll use Socket.io to broadcast real-time notifications to connected clients. In the last screencast, we learned about Socket.io, a library for Node that provides a unified API for WebSockets and its fallback transports. We integrated Socket.io into our app, but so far we're only listening to client connections. In this screencast, we'll push notifications to clients when interesting changes occur in the app. For this example, our app will emit a message for users who are viewing either the events list page or the event details page. Therefore, we only need to open a connection if we detect the elements from either of those templates exist on the page. On the server side, there are a variety of possible notifications we could generate. For the sake of simplicity, we'll limit notifications to whenever new documents or subdocuments are added to the collection. In order to broadcast these notifications, we need to update our REST API to emit events when certain actions have been performed. To accomplish this, we'll import the events module and get a reference to the event emitter object. We also need to import the util module. Now, instead of exporting each of our REST API methods individually, we'll encapsulate those methods in an object. As you can see, we decoupled our models from the controller by passing them into the object as a config parameter. Before we export the object, we extend its functionality by inheriting from event emitter. Inside our REST API object, we'll make a few changes in order to trigger notifications. First, within our saveEventHelper method, if we're adding a document for a new event or adding a subdoc for a new response, we'll execute a customized callback within the callback for Mongoose's save method. By doing this, we can supply an additional message parameter to the controller actions. If the message exists in the callback to the controller action, then we'll know to emit an event. In order to listen for these new events in our app, we first need to instantiate the REST API object in app.js. Once instantiated, our API can be used to assign callbacks for routes exactly as we did before. And now that we've extended our module to emit events, the socket manager can listen for those notifications. Each listener will subsequently relay the same event to the socket. In the case of responses, we won't trigger a notification unless the ID of the event being updated matches the ID of the event being viewed by the client. On the client side of the socket connection in main.js, we'll show a notification message whenever one of the events gets fired. Notice that whenever we open a connection on the event details page, we send a message to the server with the ID of the event. This is how the server is able to prevent irrelevant notifications when a different event gets updated. To avoid connection errors, we'll automatically disconnect the socket whenever the page starts to unload. To test that client connections display notifications in real time, we'll view the app in two different windows. First, we'll verify that a notification appears in the events list as soon as a new event is created in another window. Next, we'll confirm that a notification appears when an event is updated with new responses. If a different event gets updated, the notification will be suppressed. In this screencast, we refactored our REST API to emit events when documents are added to our MongoDB collection. To show visual notifications for these events in real time, we utilize Socket.io to send messages between server and client socket connections. In the next screencast, we'll learn how to namespace our sockets and dynamically update portions of the page with new content. In the last screencast, we modified our real-time app to send notification messages from the server to connected clients. Although it's helpful to know about updates as they become available,
the user still needs to refresh the page to see the new content. In this screencast, we'll enhance our app to publish content updates so that the client can render changes to the views asynchronously. We'll also refactor our implementation by restricting our sockets to different namespaces. With socket.io, we can pass data to client connections that can be used to make live updates to the page. This data can take the form of either raw JSON or fully rendered HTML. The latter solution is more convenient because server templates can be reused to render new HTML. However, we'll choose the former solution since it helps conserve server resources. With this approach, the client will use a data object from the server to render parts of the view on its own. We can still take advantage of templates for rendering HTML on the front end, but we'll need to add the EJS templating library to our page layout. For this example, we'll create two new templates, one to render a list item and another to render the response lists. New events will simply be added to the event list as they get created. Since showing new responses requires more complex display logic, we'll update all the response lists at once instead of trying to make discrete changes. In order to populate these templates, the message objects we transmit to the client need to be augmented with additional properties. To do this, let's take another look at the Save Event helper in our controller. When new events are created, we just need to pass along the ID and title of the event. When a new response gets added, we'll add all the data required to re-render the response lists. Now that we've modified the payload coming from the server, we can use that data to update views on the front end. In main.js, we'll load the appropriate client-side template and render it using the message object. We'll then use the resulting HTML to dynamically update a portion of the page. This will ensure that any newly created events will be immediately reflected in the event list page without requiring a browser refresh. New responses or new response lists will appear automatically too. Since we're updating the DOM, we'll need to assign new event handlers. Our real-time app is currently configured to use the default namespace for all socket connections. If we ever decide to integrate third-party code or share our code with a broader development community, it's a good idea to use namespacing for our sockets. Namespacing also enables socket.io to reuse a single socket for multiple connections. This will require some minor changes on both the server and the client. In app.js, instead of generically listening for any connection, we'll listen for connections associated with specific namespaces. In main.js, we can create a socket connection using one of these namespaces, depending on the page context. In this section, we learned a lot about socket.io, a Node library for building real-time apps. By leveraging this unified API, we were able to enhance our server to exchange messages with connected clients. In this screencast, we dynamically updated fragments of the page with new information as it became available from the server. Now that we've completed the functionality of our app, in the next section, we'll write unit tests for it using Mocha, a JavaScript test framework for Node. Over the past two sections, we built an application in Express for a simple RSVP system. We can make sure that our app continues to function as expected by writing automation tests. In this screencast, we'll install the Mocha test framework and start validating the functionality of our app's API using Supertest. Although we focus on integration tests in this section, ideally we would include unit tests for the modules in our app. While integration tests ensures that our app is operational, unit tests help pinpoint exactly where our app might be breaking. While building our app, we could have followed a test-driven workflow, where we write tests first and then fill in the functionality piece by piece to make all the tests pass. It takes a different mindset, but writing tests first can save you a lot of time in the long run. Although the examples in this tutorial don't use sign-on, you can use it with Mocha to monitor how your functions are being called in your code. Spying can be a powerful tool for expanding the test coverage of your app. Let's get started by installing Mocha. It's a good idea to install it globally so that it can be used from the command line. Since our testing libraries will only be used for development, we'll add them as dev dependencies to our package.json file. In addition to Mocha, we've included two other libraries. Should.js is a BDD-style assertion library, which will give our test cases a more readable syntax. Also, we have the Supertest library, which is for writing integration tests against our HTTP server. To install these dev dependencies,
we'll run npm install. Note that dev dependencies won't be included when installing with the production flag. Mocha expects test to be within a directory named test, so we'll create it within our project's root directory. For convenience, we can create a file in this directory named mocha.ops to customize Mocha to run with special options. In this case, we'll configure Mocha to use should.js as its assertion library and spec as its visualization plugin for test reporting. Next, we'll create a subdirectory for integration tests. Inside this directory, we'll create a file named event.rsvp.test.js. At the top of this file, we'll set the node environment variable to make sure our app is run in test mode. Initially, the only module we import will be our app. We'll be writing tests for two different suites, one for events and one for event responses. Inside these suites, we'll stub out 10 test cases. We can run these tests from the command line by passing the test file path to Mocha. To make it even easier, we can create a makefile to search for test files and run them automatically. With this makefile in the root path of our app, running make test will run any files inside the test directory that end with .test.js. Following npm conventions, we can add this command to the script section of our package.json file and instead run npm test on the command line. Integration tests won't do us much good without a database, so we'll create a new one just for testing the RSVP app. To connect to this database, we'll create another configuration file. In app.js, we'll load this file whenever we detect we're in the test environment. Exposing the database to our test file is as simple as exporting a variable. The only problem is that our database connection is made asynchronously. Luckily, we can refactor our database interface module to inherit from event emitter, and then fire an event as soon as the database is connected, and pass the connection to the callback. Now that our DB Connect module is an object, we have to instantiate it after importing. We'll assign that object to a local variable and export it as a property of our app module. Within our test file, we'll stash a reference to the database interface object and create a variable to store the connection. In our first suite of tests, we can define a function to be called before every test runs by using Mocha's before each method. Here, we can listen for the connected event for our app's database. Once connected, we'll store a reference to the connection. Since each test will need to be run with a fresh database, we'll create a helper function that not only listens for the connection, but also clears out all the collections. Both suites will call this helper before running each test. Now if we run the tests, we'll see a log message for the database connection. To avoid cluttering our test reports with log output, we can refactor the app to use a logger module that suppresses log or error messages when running in the test environment. In this screencast, we stubbed out some tests and refactored our database interface so that it can be used with our test suites. With this foundation in place, in the next screencast, we'll learn how to write integration tests for our app using HTTP assertions. In the last screencast, we installed the Mocha test framework and updated our app to run automated tests. In this screencast, we'll create fixtures for commonly used test data and flesh out our integration tests with assertions. Let's begin by reviewing the structure of our test file. Using suites improves code organization and gives us a more readable test report. For each test case, we declare exactly what each outcome should be. Adding assertions will ensure that the underlying functionality works as expected. Before we can start writing the test, we must import the supertest library and assign the imported module to a variable named request. This will enable us to simulate requests to our app as if someone were interacting with it in a browser. Next, we'll stash a reference to our app, since supertest needs to be passed in Express app in order to make requests. We'll also initialize our fixtures object and define variables for a few common date values to be used in our fixtures. Finally, we'll create a helper function to populate our fixtures object. This helper will be executed before each test runs. So far, our fixtures consist of two test objects, one to represent an event model, and another to represent the response body of a form submission. Now we're ready to write our first integration test. We'll start by initiating the request, which requires us to pass the app to supertest. We'll continue writing the test with a series of chain commands.
The next step is to invoke the HTTP action, passing in the route we want to test. Since our controller is expecting data to be submitted as a part of the form post, we'll use the send method to pass the fixture we defined above. Calling the end method will make the request. Within the callback, we'll be able to confirm that the status code for the response is 302 for a redirect. To test that an event was successfully created, we'll need to query our test database. To accomplish this, we import the event model into the test file. After finding all the documents in the event collection, we assert that only one document exists, and that its properties match the values we sent with the request. If we kick off our test runner, we'll see that the test passes. For the next test, we want to make sure that we're able to create an event with a default date. This test looks very similar to the first. The only difference is that we modified the date field of the fixture to be an empty string. Since our model should set the date to the current time, we assert that the date for the created event occurs before the time when the test is run. This time, if we run our tests, we'll see a problem. Instead of a 302, Supertest detected a 200 status code. Assuming that an error occurred, we'd expect to see a 500 status. So let's make sure our error handler is returning a 500 status code for validation errors. It looks like it's missing, so let's add it. Running our tests again, we can see that a validation error did indeed occur. The problem lies in the date validator for our event model. The validation will always fail for defaulted dates due to a race condition. If we compare the defaulted date to the current time minus a second, our validation and our test will both pass. The assertions for the rest of the tests in this suite will follow a similar methodology as the first two tests. After executing each request, we check for the correct status code and, if necessary, the appropriate database changes. Notice that for updating and deleting an event, we manually save an event in the database before simulating the request. Before writing tests for the next suite, we first need to add fixtures representing the model and submitted form data for an event response. Since any new response depends on a pre-existing parent document, each test in the second suite creates an event before making a request. In the case of deleting a response, we add a response to the event fixture, save it to the database, then verify that it does in fact get deleted. Now that we've added HTTP assertions to all our tests, let's run npm test one last time to make sure everything's still passing. In this screencast, we use the Supertest library to test the functionality of our event app by simulating interactions with our server's API. With the help of a simple fixtures object, we were able to populate and modify test objects for submitting form data or manually saving documents in the test database. By adding assertions to our test cases, we confirm some fundamental assumptions about our app's behavior. As it turns out, one of our tests highlighted an issue with the date validator in the event model.